All right, welcome to Physics 221. I'm sorry we can't meet face to face. I certainly want to congratulate Emily. She got married. If anybody else has anything interesting, let me know so we can talk about it. So the first chapter we're going to do is chapter 14, which is fluids. So this is what we'll be doing this semester. Fluids, waves, superposition of waves, wave optics, ray optics, relativity, foundations of modern physics. Now we do then quantum mechanics, quantization, wave functions, one-dimensional quantum mechanics, and then nuclear physics and a little bit of atomic physics. A lot of the atomic physics you'll learn in chemistry, so I'll skip some of that. I'm assuming you've already read the syllabus. I'm not going to talk about it all. I'm just going to get into chapter 14, fluids. All right. So fluids. Here are the learning objectives. We want to understand pressure in fluids. And here's the important thing. A fluid is a liquid or a gas. So that's what we're calling a fluid, liquids and gases. We're going to practice using a variety of pressure units. Pressure is kind of interesting. There's a metric system unit, which we'll talk about. It's called a Pascal. But there's many, many more units of pressure, especially in the United States, sorry. We're going to learn about Archimedes' principle and talk about buoyant forces. Now, these three just have to do with fluids at rest. Then we're going to talk about moving fluids. So we'll use an ideal fluid model, which doesn't work for blood, to study fluids in motion. And we're going to skip the section on solids because it's boring. Just kidding. All right, so here's pressure. So what we're talking about, just imagine this is a small area, dA, and we have a perpendicular force applied to it. That's dF perpendicular. So that's pressure, dF over dA. So it's pressure divided by area. Now, come on, force is a vector, right? So why is pressure a scalar? Well, it's simply because this is always the perpendicular component of the force. All right? So basically, fluid pressure always acts perpendicular to any surface at all. It doesn't matter how the surface is oriented. Okay? So pressure doesn't have an intrinsic direction. It's always the perpendicular force. So it's a scalar. And what's important to realize is that the force due to fluid pressure also pushes against all parts of the fluid itself. So pressure exists in all parts of the fluid. All right, now we're going to just learn some things about pressure. So here's a question. So just pretend we're in class. So what I want you to do is, read this, pause the video, think about it, and then choose an answer. Don't cheat, all right? Don't just go forward and look at the answer. That doesn't help you. It doesn't help you think. So pause the video and come up with an answer. All right, so here's these little pressure measuring devices. So this is just a spring, right? And this is a movable piston. And so if there's a lot of pressure here, it'll compress the spring. Okay, so the question is, there is pressure everywhere. Okay, there's pressure everywhere in a fluid, in a liquid and in a gas, not just at the bottom or at the walls of the container. There's pressure everywhere. Okay, the next one. So again, pause your video. All right, so the pressure at one point in the fluid depends on the orientation of the pressure measuring device. Now, I just told you the answer to this 3 minutes ago. It's false. I mean, what did I say? It's the same. Yeah, okay. It's the same, right? The pressure at one point in the fluid is the same, whether you point the pressure measuring device up, down, sideways, whatever. The fluid pushes up, down, and sideways with equal strength. Okay, remember, pressure doesn't have a direction of its own. It produces a force dF perpendicular, which equals PdA, in any direction. Okay, now we're talking just about liquids. And you can answer this question just based on your experience in the ocean or in a lake or in a pool. In a liquid, the pressure does what? So pause and think about it. Okay, so in a liquid, the pressure increases with depth, right? When you're swimming and you go low, deeper and deeper and deeper, you can feel more and more pressure. So in a liquid, the pressure increases with depth below the surface. All right, how about a gas, though? So all we're talking about now is in a lab-sized beaker or something like that. All right, so just a little beaker. So the pressure does what? So pause. Okay, in a gas, the pressure is the same. The pressure is the same at all points. Again, we're just talking about a beaker. We're not talking about the atmosphere or something like that. Just in a lab-sized beaker. All right. So what we want to do now is we want to talk about liquids, just liquids. And we want to learn about the effect of gravity on fluid pressure. Okay, so we know that pressure increases with depth. We just said that and you know it from your experience. So what we want to do is figure out how does pressure increase with depth. So this is a beaker full of water. So this is just water that's not moving, it's at equilibrium, and we just want to consider this little section of water. So I mean, it's all water, there's nothing special, but here's just this little disk of water. So we want to just consider that disk of water. So this tiny little disk, so the mass of this tiny little disk is dm, the cross-sectional area is A, and the height is dh. Okay? So here we go. So again, we want to figure out an equation to see how pressure varies with depth. Okay, equilibrium. The sum of the forces equals 0. So that means that the forces pointing up equal the forces pointing down. All right, well, what do we have that's up? Just this. What do we have that's down? That and that. Okay, so let's do it. So we have P plus dP A, right? I mean, think about it. Remember, pressure is force over area, right? So therefore, force is pressure times area. So here's pressure times area, pressure times area. So that's up, and that has to equal the forces going down. So that's PA plus DFG. All right, now DFG, that's gravity, right? Now, what's gravity? What's a gravitational force? mg. But we're saying that the mass is dm, so we're just going to say that this is g times dm, right? Mass times gravity. Okay? All right, now, we're supposed to be finding an equation for the pressure as it varies with depth. Is there a variable for depth here? No. So that's not a good situation, right? So what are we going to do? So we've got to get a depth variable. So this is what we're going to do, and we're going to do this lots of times when we talk about fluids. So from your chemistry classes, you'll learn that density is mass over volume, right? So here, we're going to say that density, the mass is the dm, right, because it's just a tiny little piece of water that we're looking at, and the volume is dV. Now, this is uppercase V. It means volume, not potential, people in Physics 220. Okay, well, therefore, if this is true, then we can say that the mass equals the density times the volume. Yeah? So we'll do that a lot. So we're going to substitute here. For dm, we're going to have rho dV. Now, that still is not good. We still don't have a variable for the depth, but what's the volume? What's the volume of this disk? Well, it's just the cross-sectional area A times the height dH, right? So I'm saying that dV is just A dH. All right, so let's put it in. So we have an A and a dH. Now H, is that's going to be our depth variable. Okay? All right, so here we go. So we have PA plus AdP equals PA plus G rho. That's a rho, not a P, rho, right? Greek rho. AdH. Okay, so kill that, kill that, kill the A's. So what do we have? So we have dP equals G rho dH. All right. Whenever you see an equation like that with the derivatives, what do you want to do to it? You want to integrate it, of course. So we're going to integrate it. G and rho are constants, so we can pull those out of the integral. Now, we've got to be careful. This is the pressure, right? And so we want to compare the pressure at this depth to the surface pressure. So we're going to integrate from the surface. We can call that P0, all right? P0, the pressure at the surface. And here, we're going to just call it P final. And then the height, not the height, the depth. The depth, again, so we're going from here to here, right? And so the depth, so the depth here, H equals 0, and then here just some H final or something like that. We'll call it D for depth, then I won't make any mistakes calling it height or something like that. All right? So the pressure is being integrated between the surface and the PF, somewhere in the beaker. And the depth is going from the surface, H equals 0, or D equals 0, whatever you want to call it, to some D. Okay? All right. Now, okay, so what's the integral of dP? P, but we're going from here to here. So this is just P final, somewhere in the beaker, minus P0. Okay, what's the integral of dH? H. So it's just G rho, and then we're going from D to 0, so it's just D. Agree? All right, so that looks funny, so let's do this. So P final equals P initial plus G rho D. So there you go. So that shows you that pressure varies linearly with depth, right? Pressure equals the pressure on the top plus G rho D. So this is a linear equation. Pressure varies linearly with depth. So if you double the depth, you double the pressure. And again, this P0 is the pressure at the surface, right? When H or D is 0, it's the pressure at the surface. Okay, now this is a big deal. There are not a lot of equations in this chapter. This is a very important equation. So let's discuss it. All right, so there it is, right? So what I mean here is the pressure is a function of D, right? Pressure varies with D. So pressure equals P0, the pressure on the top, plus rho GD, where D is depth. Okay, special case. Let's say that the surface of the liquid is open to the atmosphere like it is here. Well, then what's P0? It's just atmospheric pressure, right? So if the surface of the liquid is open to the atmosphere, then the pressure equals atmospheric pressure plus rho GD. Okay. Now, this depth can be sometimes confusing, so I want to go over that. So here's a question for you. So pause your video and choose an answer. All right. It's actually the pressure here is equal to the pressure here. Everywhere along this horizontal line, the pressure is the same because the depth is the vertical distance from the surface of the water to this horizontal distance. Let's read that. So the pressures at A and B are the same since both points are located at the same vertical distance, 5.5 meters beneath the surface of the water. So in other words, this is completely irrelevant. Okay? Doesn't matter. Here's another way to think about it. If the pressure here was not equal to the pressure there, that means that the liquid wouldn't be in equilibrium. So what would it mean? That mean the water would be moving around, right, until it reached equilibrium. And when it finally reaches equilibrium, what does it mean? It means that pressures have to be the same, right? So basically, any horizontal line you draw beneath the surface, the pressures are going to be the same. Okay, here. Get ready to vote. Okay, here's the surface. This line is the horizontal line. The distance here, again, so this is the surface. Draw the horizontal line. And so isn't this distance the same as that distance? Sure is. So it's true, all right? It's true, okay? That's what we mean by the depth D. Okay, this is kind of neat. So you can see that the shape of the cylinder is completely irrelevant as well. So, you know, here's the surface of the liquid. This is the same vertical distance as that, same as that, same as that. I don't care about this loop and all that stuff. All we care about is the vertical distance, D. So by this equation, you know, P0 is the same, right? These are all open to the atmosphere, so this is just atmospheric. Okay, same liquid, same density, gravity is the same, the vertical distance D is the same, so the pressure is the same. You just draw that horizontal line, pressure is the same. All right, not yet. Okay, now I got to do a demonstration. I don't know how I hope this works. Hope I don't make a mess. Okay, so this is a graduated cylinder. Has a hole here, here, and here. So, oh boy. Sam, can you help? Okay. I forgot. I can't do this by myself. Okay, so come over here, grab this. Okay, if you can put your finger here and pour the water in at the same time. So put your finger in here. Yeah, put your finger there. So, yeah, now pour the water in the cylinder. Oh, I don't know how far it's going to go. Maybe we won't need your finger. Oh, darn, I guess we don't need your, okay, thanks. All right, thank you, sir. Okay, now, so where's the pressure the greatest? Here or here? Well, it's pretty obvious, right? Here the depth is greater, so what's going to happen? You ready? Please go into the trash can. Woo! All right? Does that make sense? The greater pressure is here, so the greater force, so it's going to go further. Thanks. All right. Okay. All right. Here's a question for you. So this is not an easy question. So think about it and get ready to vote. All right. And pause your video, of course. When a hole is made in the side of a container holding water, like this thing, right? Water flows out and follows a parabolic trajectory. By the way, why did the water follow a parabolic trajectory? Well, once the water leaves the container, what's the only force acting on it? Gravity. Therefore, what kind of motion is this? Free fall. All right, okay. So when a hole is made in the side of a container holding water, water flows out, follows a parabolic trajectory. If the container is dropped in free fall, what happens? So if we were meeting face to face, I would take a ladder and I'd go outside and I'd climb to the top of the ladder and I have a little cup with a hole in it and I'd fill the cup with water and I would hold on to the cup. So I'd hold up, I would, keep the hole covered up and then I would drop the cup and you figure out what would happen. Okay, and I gave you a huge hint. So the pressure varies with depth. So the pressure at any depth equals atmospheric plus rho GD. But what's G? It's just acceleration of gravity, right? right? You know, A sub y. So here's what you want to think about. When you're dropping the cup in the reference frame of the cup, what is A sub y? It's a Physics 121 question. According to the cup, in the cup's reference frame, when it's dropping in free fall, what's A sub y? It's 0. Okay, it's 0. So therefore, this goes away, and therefore that equals that. So what's going to happen to the water? Nothing. All right, the water does not fall out of the cup. In other words, you know, like if I had this filled with water, and I had tape on these holes, and I drop this from the second-story building or something like that, and as soon as I take the tape off and I drop it, no water would come out of this thing, because in the reference frame of this, the acceleration of gravity is 0. It's kind of like, you know, if you were on LeA point and you jumped off, and let's ignore air resistance. So you jump off LeA point, and you have this little remote control thing, and you drop it. When you're falling off of LeA point, what's this going to do? It's just going to go with you, right? So does it look like it's falling relative to you? Not at all. Not at all. Okay? Anyway, so think about that. Good Physics 121 question. All right, this is a tough one. So pause your video and think about it. I give you a huge hint. This is in a different color. There's probably a reason for that. So pause your video and think about this. This is not easy. Okay, so I'm assuming you paused. All right, remember, any horizontal line equal pressure. But the thing is, all right, so right here, equal pressure. However, what's the density of the oil relative to water? It's less, right? It's less. So, okay, so atmospheric pressure is the same, right? Both here and here. And the pressures here are the same. So we have, on the left, we have pressure equals P0 plus rho GD, right? Okay, so this is true along that horizontal line. Well, this is the same, that's the same, so this has to be the same, right? So we have rho GD oil equals rho GD water. Now, G is the same, goodbye, but the density of oil is less than the density of water, so if rho D oil equals rho D water, and this, right, density of oil less than density of water, then this has to be bigger than that, right? So that's why you see that the depth of the oil is greater than the depth of the water. All right. Okay, I'm beating this to death. So here's one more question, just to make sure you get it. So pause your video and answer it, please. Okay, again, each of these locations, A and B, are at the same vertical location, vertical distance from the surface of the fluid, and so it's equal. And again, if the pressures were not equal, this fluid would be moving, right? The fluid here would be moving until they establish equilibrium. When they establish equilibrium, the pressures would be the same. All right, let's see. Let's quit. So that's enough for now.